Okay, now we are in part B. We're talking about potential across the plasma membrane and voltage and learning some basic principles of electricity so that we can understand an action potential. So, on the current slide, we're learning some basic principles of electricity. We already talked about insulators and conductors. A conductor is something with low electrical resistance, so electricity flows freely through that. And an insulator, like the insulation around the wiring, in your house, is a substance with high electrical resistance. That way, when you grab it, the electricity doesn't flow very well through that. So it insulates the electrical current from contacting your hand. Okay, in electricity, Ohm's law is defined as the relationship between voltage, current, and resistance. Now, current is the flow of electricity. Voltage is the measure. That's the unit that we use to measure how large the electricity is. And then resistance is the amount. It's kind of opposite to current. It's how much. When it's high, electricity flows fast, and when it's low, electricity flows slow. So current is flow. The current is equal to the voltage divided by the resistance. So the current, I'm sorry, I'm just looking to see if there's a word that starts with I. I don't know with this. I haven't done this in so long. I'm not sure if it's got to be a capital I. So current, capital I, is equal to voltage divided by resistance. Okay, what that tells you when you look at that relationship is that current is directly proportional to voltage. So the greater this number is, the greater this number is going to be. It's inversely proportional to resistance. So when resistance is low, then current is high. Membrane ion channels. These are large proteins within the plasma membrane, the phospholipid bilayer, and they are selective as to what they will allow to cross over the membrane. For example, ion channels for potassium only allow potassium to pass through. There are channels for potassium, for glucose, for sodium, for chloride ions. Some channels are what we call leakage or non-gated channels. These don't have anything stopping the ions that can pass through these channels. Would just pass through them by diffusion. Sorry, they just pass through from their high concentration to their low concentration. So they're always open. Leakage channels or non-gated channels are always open to the substance that is allowed to pass through them. Gated channels, which we will deal with quite a bit, this is a channel that only opens or closes in response to a stimulus. If it's chemically gated, like for example, the sodium channels located on the motor end plate in our last chapter, or in our last topic, muscles, that sodium gated channel did not allow sodium to come into the muscle until acetylcholine binded to that receptor. So that's chemically gated, is when it's controlled by the binding of a neurotransmitter to a receptor. And it's voltage gated when a change in voltage causes it to open or close. And it's mechanically gated when it's something like a trigger mechanism, when a touch, some type of touch, or it's a physical thing that opens the gate. An example of mechanically gated would be like the simplest one would be those chain link fences, and they have that little part that's like this. All right, and here's the post, and you just kind of, and then this is connected to another post, and you just kind of lift that up. Yes, my drawing is awful, but that's mechanically gated. You open the gate by mechanical means, just physically somehow, and it can be a trigger mechanism as well. When something hits the trigger, it opens, that kind of thing. So mechanically gated often opens in response to physical deformation of the receptors, as in sensory receptors, because when we touch something, the sensory receptors change shape, and they are able to send that touch information to our brain, so we're aware of what it feels like. Now, here's an example of a chemically gated ion channel. We could say that this neurotransmitter is acetylcholine. It can be any neurotransmitter, but acetylcholine binds, and this causes two things to happen. It causes sodium ions to move in. Sodium is the yellow, and it causes potassium ions to move out. Now, that is the opposite of what sodium potassium pumps do. Here is an example of a closed sodium channel that, in response to a voltage change along the plasma membrane, somewhere around here, that channel will open and sodium will move in. So a chemical triggers a chemically gated channel, voltage change triggers a voltage gated channel, and something mechanical, some way to just change the shape of the channel itself. Something mechanical changes mechanically gated channels. All right. When gated channels are open, the ions that diffuse through them diffuse quickly. They diffuse, so they move from higher concentration to lower concentration. That's the definition of diffusion. And they also move toward opposite charge. So they're going to if they're on a side of the membrane that's positive, they're going to move to the other side if it's negative. Okay, so they're going to move toward opposite charge. This is the Ohm's law equation rearranged. Voltage equals current times resistance. And a voltmeter measures voltage or potential difference across the cell membrane of a resting cell. Here, this is very important. Resting membrane potential of a resting neuron is approximately negative 70 millivolts. Very important that you remember that number. Negative 70 millivolts is the resting membrane potential of a neuron. That's the difference in charge across the membrane, and what it tells you is the inside of the membrane is negative. So this lets you know that the inside, the cytoplasmic side, is negative relative to the outside. Okay? And the membrane is said to be polarized. On one end it's negative, one end it's positive, so that's where that comes from. Potential is generated by differences in ionic composition of the intracellular fluid and the extracellular fluid. In other words, the cytoplasm and the fluid outside the cell. Differences in the plasma membrane permeability, and what that when we have gated channels to open, a bunch of gated channels to open, then the plasma membrane becomes permeable to whatever is allowed to move across that gated channel. Okay, so difference in ion composition. Where is the composition high and where is it low? And then also the amount, difference in permeability. Permeability means the amount of receptors for that ion, because it can't cross unless it has receptors. Most of these ions have a charge. They can't just diffuse through the plasma membrane. So this is such a better drawing of the one I did for you. This is the inside of the plasma membrane of the axon. Neurolemma instead of sarcolemma, but we're just going to call it the plasma membrane. The inside is negative compared to the outside. The outside is more positively charged than the inside. And that voltage across the plasma membrane is negative 70 millivolts. That is resting membrane potential in a neuron. Now, the differences that what generates the resting membrane potential is what generates it. The extracellular fluid has a higher concentration of sodium. And there's also chloride ions. They follow wherever sodium ions go because of the negative charge being attracted to the positive charge. So the extracellular fluid has a higher concentration of sodium and chloride. The intracellular fluid has a higher concentration of potassium. And then there are proteins inside the cell, large proteins that cannot move from inside the cell that are negative already. So, so you've got positive charges out here and negative charges that kind of balance each other. And then you've got large proteins with negative charges that can't move out of the cell. And so the only way you're going to change that potential is to bring some positive charges inside. Bring some of that sodium inside, and that's going to change that potential from negative to positive. And the only way you're going to get it to go in the opposite direction is the potassium that's inside moving out. Okay, so potassium is going to be the ion that plays the most important role in membrane potential. Okay, so this is just a picture that explains the sodium-potassium pump. I'm trying to blow it up, make it larger for you. Hold on. You don't really need to see any writing. You just need to see this bigger. Okay, so what this is showing you is that outside the cell, the concentration of potassium is high, and sodium is high, and it's low inside the cell. The reason for this is the sodium-potassium pump transports 3 sodium ions out of the cell and 2 potassium ions inside the cell. So it maintains that resting potential by pumping sodium out and pumping potassium in against their concentration gradient. There's already a lot of sodium outside the cell, but the sodium-potassium pump keeps pumping it out. So we say that it maintains the concentration gradient. Maintains the resting membrane potential. Plasma membrane permeability when it's at rest, impermeable to large negatively charged proteins. So they're inside the cell, they're large and negatively charged. Slightly permeable to sodium ions, but not much. And if there are leakage channels for sodium, sodium is going to come in, okay? So we've got our large proteins that have a negative charge. They're all inside here. There's no permeability to those. They can't leave. And then there's these sodium ions, which their concentration is very high outside the cell. There are a few channels that allow the sodium to come in, but not very many. And then there's a high concentration of potassium inside the cell because the sodium-potassium pump is pumping potassium in and sodium out. And so it says that sodium will diffuse into the cell down its concentration gradient from high to low, which means it's going to move in. And potassium, which the plasma membrane is 25 times more permeable to, that means that it has more leakage channels. Potassium diffuses out of the cell faster than sodium diffuses in. The cell is quite permeable to chloride ions, so any potassium that goes out, that's a positive charge going out, the chloride ions can go out too and kind of balance that. Chloride ions can come in. So a positive went out and a negative can go in, and then that's balancing out the charge. You need to know this. The purpose of the sodium-potassium pump, which is called sodium-potassium ATP ACE, is to maintain the resting membrane potential. Maintain resting membrane potential. Sodium potassium pump.